Hey students, this presentation is going to be on solving systems of equations using matrices. Now, I know that that title is kind of a lot to swallow all at once. It's going to be new material, so that means we have some new vocabulary to look forward to. But essentially, this final section or this final topic that we're going to be covering, it takes us back to linear equations. And a system of equations is basically a grouping of two or more equations that you can solve at the same time. And there's different methods for doing this. The state of Texas requires that all colleges and universities teach college algebra students how to solve systems using something called a matrix. Okay, so that's what we're going to be getting into today. We have, as always, some objectives that we want to think about. So first, we're going to go back and review a little bit about linear equations, and we're going to graph two linear equations on the same coordinate plane. Okay, so we're going to put those two line graphs on one graphing space. Then we're going to review some of the possible outcomes of what happens when you graph two lines. That'll sort of lead us into and form the foundation for the matrix concept, which is going to be very new. So at that point, the matrix concept or solving systems of equations with matrices, that's really what this homework is going to be all about in ALEX. So I want you to pay attention to the main ideas or like the big picture in the first discussion that we're going to have. But then the second half of this PowerPoint, once we talk about matrices, their dimensions, converting systems of equations into matrices, then that's when you're going to really want to take note because that's going to be directly relevant to the homework you're going to see in ALEX. Okay. So let's begin. All right. What is a linear equation? Well, you guys should be familiar with what a linear equation is because the most famous form of a linear equation that you guys have learned since high school is y equals mx plus b. Okay, remember now, I kind of prefer to put ax plus b, but if you want for your own benefit, you can change that a into an m. It doesn't matter what we call that coefficient. What matters is that you understand that the m refers to the slope of the equation, and then the second coefficient or the constant in this equation, b, is the y-intercept. Okay, and the y-intercept can be written as an ordered pair. So if we're going to write that as an ordered pair, we would write it as 0, comma b. Okay, so that's going to be the location. So all y-intercepts have a 0 for the x-coordinate, and then that b, whatever that number is, that's going to be your y-intercept. Okay, so a linear equation is the most basic kind of equation, the most basic kind of function that we've dealt with this semester, because we really don't have any complicated terms that have second power, third power, fourth power. We're not dealing with a higher order polynomial, so we're not expecting a graph that's going to be wiggly. We don't have to worry about the end behavior. We don't have to worry about the multiplicity of zeros. For linear equations, we only need to find two ordered pairs in order to graph the entire linear equation. Because as long as we have 2 points, we can draw a straight line through them, and then that will be everything that we need. Okay, but we're going to have to do that for more than one equation at once. Okay, so let's take a look. Consider the two linear equations that we have here. We have y equals 2x minus 3 and y equals negative 3x plus 7. Okay. Whenever you have a grouping of two or more linear equations, we call it a system of linear equations. And we say that these equations might be able to be solved simultaneously. Okay, that just means that we can find a solution that satisfies both equations at the same time. Okay, but how would we go about doing that? So I think that the easiest way to think about this is if we go over to pencil and paper and sort of see how we do this by hand. Okay, so let's actually go over to the document and see what we're dealing with. Okay. So the two equations that we were given in the PowerPoint slides are the following. We have y equals 2x minus 3, and we have y equals negative 3x plus 7. Okay. Now, if you see a system of equations in um, like a math textbook or something, they will usually put a brace on the left side of the equation. That's just indicating that we're grouping these two equations together. But we have this system or grouping of linear equations. And if you think about this, these are just functions. You can just look at them individually and graph them. Okay, so we'll graph these the way we always graph them. We kind of want to solve them graphically, and we'll see what we mean by solution. We'll see what we mean by solving graphically here in a moment, but you guys should know how to graph these. So what I'm going to do is sort of color coordinate my graphing process. So this first equation, I'll label it equation 1. I'm going to set up a table, x and y. And as always, the y value is determined by this equation. So we have 2x minus 3. And as it should be familiar at this point, you should be able to choose any x values here for your equation to plug in and get the y values. Okay, so I like to choose some small numbers. 0 and 1 will be good, but anything will work here. Okay, so if I choose x equals 0, I can put 2 times 0 minus 3 into my calculator. 2 times 0 is 0, minus 3 is going to give us a negative 3. So that means I have the ordered pair 0, comma, negative 3 here. Okay, I'll do the same thing for 1. So that x value of 1, we're going to plug into the equation. So 2 times 1 is 2, minus 3 is going to be a negative 1. So we have 1 comma negative 1. That's our second ordered pair. Okay. So now we're going to do the same thing with the second equation, equation number 2. And so we're going to label that in red here. So I'll put x and y. This time the y values are going to be determined by the second equation, which is negative 3x plus 7. And we'll just choose some small values like 1 and 0 again, and plug them into this equation now to find these y values. So we'll put negative 3 times 0 plus 7. We'll put negative 3 times 1 plus 7. And then we'll just compute what these y values are. So this one should be 7 when we put this in the calculator. And then negative 3 plus 7 would be 4, positive 4. Okay. So now I have a pair of coordinates for my first equation and my second equation. Once you get those, as always, we're just going to go ahead and draw a coordinate plane. So we have our x-axis and our y-axis. And we want to be careful, with our labeling here because our y values go up to 7. So we want to at least go out 7 spaces. So I'll go out 1, 2, 3, 4, 5, 6, 7. And I'll go up 1, 2, 3, 4, 5, 6, 7. We'll go to the left 1, 2, 3, 4, 5, 6, 7. And then we'll also go to the downward direction 1, 2, 3, 4, 5, 6, 7. Okay. Okay. So let's go ahead and plot these points. For this blue color-coded graph, equation number 1, we have the ordered pair 0, comma, negative 3. So 0, negative 3 is going to be down 1, 2, 3 right here. And I can go ahead and label that point as 0, comma, negative 3. We have 1, comma, negative 1, which is over 1, down 1. And that is 1, comma, negative 1. And you can see that this line seems to be going up. Okay. If we wanted to, we can grab a straight edge and then draw a straight line through these. But if you are feeling kind of uncomfortable with just 2 points rather, if you notice the slope of this first equation is 2. That's a positive number. And if you remember that slope is equal to rise over run, then 2 can be written as 2 over 1. So that means that we could just go up 2 over 1 to sort of get to the next point. So if we go up 2 over 1, we get to this point here. We can go up 2 over 1, we get to the next point there. And so with a few more points, you can be a little bit more confident that you're going in the right direction here. So as best I can, I'm just going to draw a straight line passing through those points. And that's good enough for government work. It doesn't have to be perfect because we're not robots, okay? So there's our equation, 2x minus 3. And now we can graph the other equation that I'm going to do with a red pen, okay? So we have 0, 7, which is our y-intercept up here. That makes a lot of sense because this right here is the y-intercept, right? So 0, 7 should be correct there. And then 1, 4, which is over 1 up 1, 2, 3, 4. Okay, so that's 0, 7, and that was 1, 4. And then we could also use this slope to figure out another point if we wanted to do that, because this slope is -3. That's the same as -3 over 1. So that tells us that we're going to go down 3 over 1 from the previous point. So if we go down 1, 2, 3, and over 1, we'll be overlapping this point right here. And really, we just needed 2 points, but 3 points is better. We'll go ahead and draw a line that is crossing those points as best we can. There we go. And there are our 2 lines that represent our 2 equations, okay? Well, if you just look at this graph, the interesting thing about it is that we have an intersection point right here. That's where our 2 lines intersect. And if you look at the graph, it looks like it's at about the coordinates 2, 1. 2, 1 is where those intersect. And so actually that is a very important point because the point or the xy pair 2, 1 is the solution to the system of equations. Okay, so what do we mean by solution? Well, in math, when we're talking about equations, we have said in the past that a solution is a number or a set of numbers that when you plug into the equation, you get a true statement. So if our solution set is 2, 1, that ordered pair, you have to remember, this is an x value, this is a y value. And each of these equations has an x and a y variable. So like for instance, if we go into equation 1, which was 2x minus 3, y equals 2x minus 3, sorry, and plug in the x value and the y value, we have 1 for the y value equals 2 times 2 was the x value. Okay, so all we're going to do is plug in this set of ordered pairs, right, this x and y value into your equation, and then we're going to simplify both sides. There's nothing to do with this 1, but over here on the right side of the equation, we have 2 times 2, which is 4, minus 3, which is 1, and you can check that in the calculator. We have 1 equals 1, which is a true statement. And so that means that the ordered pair 2, 1 is a solution, or sometimes we say it satisfies the equation 2x minus 3, or it satisfies equation number 1. Okay, and that's because we got a true statement when we plugged in the x and the y value. Okay, but in order for this point to satisfy both equations simultaneously, then we should be able to plug these same ordered pairs, the x and the y, into the second equation. So that was y equals negative 3x plus 7. And if we just plug in y, which is 1, equals negative 3 times 2, that's our x value, plus 7. And then simplify this, we'll see what we get. We have 1 is equal to negative 3 times 2 is negative 6. And then if you add 7, you get a positive 1. So that also is a true statement, meaning that 2 comma 1 is a solution for equation number 2. And so since it's a solution for both of those equations, we say that that point, that xy pair 2 comma 1, is a simultaneous solution for both of the equations in our system. In other words, 2 comma 1 is the solution for this system. Okay, so let's switch back over to the PowerPoint just briefly, kind of to recap what we just looked at. Okay, so what we did was we set up two tables and we chose X values so that we could graph them, so that we could find the Y values, get some ordered pairs, and then produce a graph. Okay. Once we've obtained the 2 points for each of our two linear equations, we plotted them by hand in a Cartesian coordinate system. Okay. You could also throw those equations into Desmos. That would be perfectly fine. In fact, you would probably see a much better picture because if your graph is a little bit off, sometimes it's a little bit wonky when we draw these things by hand. Desmos is going to produce a perfect representation of these equations. In any case, we can see right here that those two lines intersect at the point 2 comma 1, which is exactly what we found. Okay. So the solution of a system of equations, which in our case was 2 comma 1, is the intersection of those two line graphs. And the good news here is that we're only going to be studying linear equations. So that means that we need to think about all the possible arrangements of two lines in space. Okay. So for any set of two arbitrary linear equations, will the lines always intersect? Well, that's not necessarily going to be the case. So we have to watch out for three possibilities. The first possibility is that we're going to have two lines that do intersect, in which case we would call that intersection point the solution to the system of linear equations. Okay. Possibility number 2 is that you could have two parallel lines. And if you remember from grade school, two parallel lines will never intersect each other. Okay. We say that the system has no solution or that the system is inconsistent. Okay. And a third possibility is that you graph both of the lines and the points are exactly the same. So what I mean by that is when you graph both lines, they have the same XY pairs. And so if you were to put them on a graphing space, it's like the lines are laying right on top of each other. In other words, they are the same line. Okay. So one way that you could just kind of visually inspect the equations to determine whether or not you're going to run into this possibility is if one of the equations is a multiple of the other, then they're going to overlap. Okay. But most of the time, we'll just go through the process of finding the X values or choosing the X values rather, finding the Y values and then graphing them. And if all of the ordered pairs are the same, then we're going to say the system has infinitely many solutions. Okay. So those are the three possibilities that we want to look out for. And I'm going to go ahead and stop right there. This has been kind of like a preview for what we're going to be getting into as far as matrices are concerned. But this is the big picture because a lot of times in algebra, we do some stuff with some math. We kind of lose sight of why are we pushing these numbers around? What does the solution mean? But once we get into matrices and you might lose kind of the big picture, you always have to bring it back and remember that the two equations that we're dealing with represent two lines in space and that they may intersect each other. And if they do, that intersection point, that XY pair, is what we call the solution for the system of equations. We'll pick back up on another video where we really get into matrices. Okay, so look forward to that.